Yeah.
Okay, let me check my pen is working now. Okay, good. Let me change the color. Hold on. So let me read the first problem. Problem 12 in figure 11-35, the one below this description. Solid brass ball of mass 0.28 gram will roll smoothly along the loop track when lead from the last along the straight section. The circular loop has a radius r 14 centimeter, and the ball has radius r much smaller than radius of track. So the first question is, what is h if the ball is on verge of leaving the track when it reaches the top of the loop? If the ball is released at height h, the 6r, what are the magnitude and the direction of the horizontal force component acting on the ball at the point Q? So it is a typical actually case using the energy conservation because in given condition, the ball rolling straight section, and most likely if you see that the one of the condition include the height of starting point, I bet you that's probably the typical case of the problem you know using the energy conservation. So you can start with some basic formula with the kinetic energy and the potential energy, especially for rotational motion. The kinetic energy split into translational kinetic energy and the rotational kinetic energy. So let's take a look. So as I said, this is typical problem of energy conservation. So you pretty much understand this situation, right?
Yeah.
Okay. So we got to use energy conservation. So when that ball release, there's only potential energy. So we don't have to worry about the kinetic energy when ball is just released from top. And that when the ball reach to the top of the circular track, then that should be split into the kinetic energy and the potential energy. So the initial kinetic energy should be expressed with the mass times gravitational constant value and the height of straight section. And that should be also expressed with the kinetic energy, the translation kinetic energy, the 1/2m V of standard mass square plus 1/2 rotational acceleration, the rotational kinetic energy. And then when this ball actually reaching the top of this track right there, that height should be mz2r, right? So that's h2, which is 2r from reference of this system. So now we have to just add the momentum of inertia for this sphere ball, and angular momentum. I mean, angular velocity should be expressed with the translation velocity of center of mass and the radius of the sphere. So if you add them together, so that the momentum of inertia of the sphere is 12.5 m mass times radius square, and the angular velocity could be expressed with the translational velocity of the sphere and the radius of that. So if we re-expressed this energy conservation equation, then that should be mgh and 1/2 mv center mass square plus 1/2. You add the value expression of I into this formula. That should be 12.5 mr square times v center of mass square over, oh, actually, over r square plus 2 mzr. Okay, that is basic formula you have to use to derive the answer for ABC question. So you take the mass out of this formula, and that could be simplified. GH equals 1 over 2 MV. Oh, actually, you can add the like first term and second term all together because basically you take off the omega out of the equation that make it first and second term as a single term. So that should be 7 over 10 velocity translation velocity of center of mass of the sphere squared plus 2 g r. Okay, so that is like the standard formula to describe the energy conservation in this kind of system. So now next step is just go into details with the more precise actually a description of the height and the sphere of ball. So number A. So now when the ball reach the top of the circular track, then the meaning that the ball, what's that condition? And now the ball is on the verge of leaving the track when it reaches the top of the loop. That means the normal force on the track should be same as gravity. So they are actually the angular, radial force component outward should be same as the force downward from the gravity. So this is equivalent, actually the equilibrium position. So from this here to here, the distance is r minus the sphere, the radius of the sphere, right? You have to just take that, the r, small r, out of that, the large r. And outward acceleration, the acceleration of the sphere while it's actually just rolling around this loop of track, then is the radial component of acceleration AR, and that also experience gravitational force downward. So this normal force Fn is about 0. That's the meaning of this one. So the ball is on the verge of leaving the track when it's reached the top of the loop. So that is, you got to use this condition to solve the problem. So gravity should be same as m r ar, centrifugal force. So ar is, as you know, that function of the translational velocity at the tangent line of translation motion divided by radius, but the radius here is r minus small r, the sphere, radius of the sphere. So this is the radius of the loop. And this is the radius of sphere. So if you replace it, then obviously the G is the B center mass square of R minus R, right? So now next step is just to add this condition into this formula, because that is like a basic formula, the backbone of the oval system dynamics. So all we need just to add this new condition into this formula, then you will find that the relationship between the h, the height of straight section, and the radius of this track. So let me just move on to the next whiteboard. So that GH equals 7 over 10 V center of mass square plus 2GR. Now you have to replace this one with the Z equal V, center of mass, V over R minus R. That's what you got from the A, condition A. So if you replace that, then that should be 7 over 10 Z R minus small r plus 2 Z R. So you rearrange this equation in terms of H, then H is 7 over 10 large R minus small r plus 2R, right? That's easy. That's straightforward. So you can just directly apply that numbers into this formula, or you can actually just approximate this one with the condition this R. One of the condition given in the problem is the radius of the sphere is much smaller than the radius of the loop, right? So that in that case, so basically this one, if you rearrange it, that should be 2.7 R minus 0.7 R, right? So here, that you have 2R, and this one is 0.7 R. So if you plug them together, that should be the 2.7 R minus 0.7 R. So either you can add that number, or that could be approximate, because this R is much smaller than the radius of the track. That should be approximately 2.7 R. So this problem, so that's approximately 2.7 R. Now the R is the given condition. What is R? R is, let's see, 14 centimeter. You plug it, then that should be H is 2.7 times 14 centimeter. So that is 37.8 centimeter. Okay. And B, now question B slightly actually just modify the condition. So the straight section H already given, the 6R. Now you have to find out the force exerted on the top of, let's take a look at the problem again. So if in the case this straight section is about 6 times the radius of this circular track, the loop, then we got to find the force, original force component acting on the ball at point Q. It's not top, actually, this middle of the actually circular track. So you can find that the outward acceleration force with the gravitational force too. So now you gotta replace the H with the 6R. GH should be G times 6R. Now, and also the right hand side of the equation was 7 over 10 V center of mass square plus GR. That should be the GR. Do you understand why the two GR just change to the GR, right?
Yeah.
Okay, that was previously was top of the circular loop, so you have to add 2R. Now it's just changed to the middle of the actual track, so that 2R changed to the R. So now if you just simplify this formula, then the speed of the this ball, the center mass square, is 50 G times R over 7. You can summarize it. You can rearrange this equation. You should be able to find this relation. Okay, so now F and normal force exerted. Oh, hold on a second. So let me just normal force acting on the ball at the point Q is this direction, right? So that track. That force should be mass times centrifugal acceleration. Then that should be M times B center mass square r over small r, right? That is at the center of mass. So this one is centrifugal force, which is same as normal force. And if you add them, you replace this center mass with this condition. You place it, then that should be m times r over small r times 50 g r over 7. We'll rearrange it. That should be m 50 g r over 7 r minus small r. So same thing. You can just plug the numbers into the formula. Also, you can approximate it with this condition. The track is much bigger than the sphere ball. So if you plug that should be approximately m 50 g r over 7 r. So that r cancel out the numerator and denominator. That only leave m times 50 g 7, right? So here mass is what? How much? What's the mass of this? Was it 280 grams, right? No, actually 0.28 grams. So the pretty small, teeny tiny actually ball sitting on the track. So that is 50 times 2.8 times 10 to the minus 4 kilogram, and g is 9.8 meter per second square, divided by number 7. So if you just plug that number, then we'll find that the answer is 1.96 times 10 to the minus 2 Newton. It's about like 20 millinewton. Okay. And number C, as I said, the normal force is only force create the, the centrifugal force only source to create this normal force. So when ball is going around this point Q, the force pointing the left hand side, that is inward of this loop. So the direction of this force is toward the center of the roof. Okay. So as I said, as always, I just uploaded this video file and PowerPoint slides in your account. All have chance to review these problems yourself. Okay. Any question?
No.
Okay, that's pretty straightforward. There's nothing special if you use the energy conservation. Okay, let's move on then. Oh, by the way, do you see my monitor? Right?
Like,
Let me double
what?
check if I turn on my camera or not. Do you see him?
Yeah. I can see.
You see it? Okay.
Yeah.
I want to double check my face inside of this camera. So let's take a look at number 14. Can you read this problem?
In figure 1137, a small, solid, uniform ball is to be shot from point P so that it rolls smoothly along a horizontal path up along a ramp and onto a plateau. Then it leaves the plateau horizontally to land on a game board at a horizontal distance d from the right edge of the plateau. The vertical heights are h1 equals 5 centimeters and h2 equals 1.6 centimeters. With what speed must the ball be shot at point P for it to land at d equals 6 centimeters?
Okay, this is also a similar problem using the energy conservation. So the ball is shot from the point P and going along this path and reach to the cliff of this track, and that's actually just to leave the verge of this cliff, and then after projectile motion is landed on this right on the track with the distance v from the cliff of this pass. So it look that the dynamic itself seems pretty complex, but if you use the energy conservation, all we need just plug that condition into the law. So when this ball, that basically doesn't matter where you're standing, that total energy should be same, should be conserved. So if you that constraint on this problem, then the total energy out of first part of this system, that is the number one, and when that ball is reached to the end of that track, that's number two. Total energy at number one and number two, they should be same, as you know. So if you plug that the kinetic energy and potential energy out of that those 2 points, then that should be 1/2 mv squared plus 1/2, that is kinetic energy translational motion, and 1/2 I momentum of inertia at center of mass times omega square of the ball, and that should be also, there should be also potential energy from the reference point. So in this problem, we can set up the top of this track as the reference point. So and that should be same as 1/2 mv p square plus 1/2 I center of mass times omega p square. So when this ball is just leaves the end of this straight section, then that starts have projectile motion. Hopefully do you remember that relationship between the velocity and the height with this kind of projectile motion in chapter, I think, 4 in linear motion of Newtonian system. In that case, the velocity when actually just leaves the cliff should be v square equals g d square of 2h. You will look back at that chapter, you'll find this formula. So the travel distance from the starting point to the landing spot is parameterized with the initial velocity v, the vertical, horizontal direction equals v. And because while this object have free fall in the vertical direction, that object itself has linear motion with the constant velocity v, x equal v naught, v. So if you plug this total travel time from here to here and here to this point D to be same. So if you use that constraint and plug the vertical motion and horizontal motion, then you'll find the relationship between the V and D. So now if you plug that into this formula, so that here H should be H2, that is on this system, second system number 2. We plug that into this formula, then that should be, now you replace this one, this, right? So that is hold on. That should be 1/2 m and v d square of 2h2 plus 1/2 also here Remember, that was from the previous example. That was, we can find that this one 10g times h1 over 7 should be, so if you yeah, that has actually, we have sphere relationship right now. So 102 over 5 m, what, m r squared times omega squared plus equals, oh, plus mg h1 equals 1 over 2 mvp squared plus, same thing here, 102 205 m r squared times omega p squared. So if you rearrange that and cancel m out of this formula and simplify it, then that should be simplified to e squared times 2h2 plus 10 g h1 over 7 is vp squared. Okay, rearrange it. If you add the omega equals p over r, then you will find that this formula out of this kind of like that long expression could be simplified into this formula. So you plug that numbers now. E is what? 6 centimeter. So that should be 0.06 meter. And H2 is 1.6 centimeter, which is 0.016 meter. And H1, 5 centimeter. So that is 5 centimeter, which is 0.05 meter. And you will find the velocity Vp. So take a square root of that, then that lead to the number. So that P should be square root of everything in, this left hand side. That should be GD square of 2h2 plus 10 GH1 of 7, which is approximately at 1.34 meter per second. Okay, so initial that velocity should shot from this point should be 1.3734 meter per second. That make this ball leave that edge and then land this straight section with the 6 centimeter distance from the cliff of this one. Okay. All right. Okay. No, any question?
No.
Okay. Let's move on then. Next one is about the angular momentum conservation. You can maybe just compare that the unique angular momentum out of different size of disk. So let me read this problem. So figure 11-43, the one on your right, shows 3 rotating uniform disks that are coupled by the belt. One belt runs around the rims of disk A and C. Another belt runs around the central hub on the disk A and the rim of disk B. The belt moves smoothly without the slippage on the rims and the hub. So disk A has radius r, its hub radius the 0.5 r, the half of the A, and the disk B has radius 0.25 r, and disk C has radius 2 r. So disk B and C have the same density, mass per unit volume, and the thickness. So what is the ratio of the magnitude of angular momentum of disk C to that of disk B? So these 3 disks they're all connected by the belt, and their angular velocity and the linear velocity is pretty much depend on the size of this individual disk with a different radius. So as you can see, the angular velocity omega A should be twice of angular velocity of the C because, well, based on the angular momentum conservation, that this A is that has a radius R, right? And it's have radius this one has radius R, and this one is the what 0.5 R, and this B has this one is 0.25 R, quarter of the radius of A, and the C, how many, that is twice bigger than the disk A. So with that idea and angular momentum conservation, then that should be also the angular momentum of A should be just half of angular momentum of B. Okay. So with that idea, you can find a relationship between the angular momentum, angular velocity of the disk B and the disk C. So you can just plug that and just then that should be 2 omega C equals 1 over omega B. And that the angular velocity of the disk C is 4 times slower than angular velocity, lower than angular velocity B. Okay. So from this, each mass. So the mass itself is the mass density low. If you just set up introduce the new parameter of density, mass density low, then that lowest mass density times its volume itself is the mass. So here, the low is mass density. This is volume. So if this disk are made out of the same material, then that should have the same density, but their volume is different because their size, radius is different. So volume of disk is the area of the cross section times the height h. So if you think of this disk as, this 3 disk has same height h and radius r, that its volume itself is the pi r squared times h. Okay. And there inside this material have the mass density low. So now if you plug that into the formula, then the angular velocity omega c over angular velocity omega b. Now you compared angular velocities out of 2 disk B and C. Then first, that same as 1 over 2, that is the I. Now let me just fully express this one. That is I C omega C over I B omega B, right? So IC is 1 over 2 M R C squared omega C, and the angular momentum of inertia of the disk B is 1 over 2 M. So M is should be C, and B, mass of the disk B times R B squared omega B, right? Now we try to just find the ratio between those two angular momentum out of the disk B and C connected by this belt. So the MC, as I already expressed, could be expressed with the volume and mass density low. Now, we already assumed that these 2 disks are made out of the same material, so their mass density should be same. So that should be 1/2 low pi r c square times h. That is mass mc and times lc square omega c. That is numerator. And the denominator is 1/2 low pi r b square h. That is m b times r b square omega b. So here, low obviously can be canceled out of the numerator and denominator. Pi is gone. H is gone. Their thickness of disk, we assume they're same for B and C. And 1/2 also just disappear. And that's leave what? The RC cube times omega C and RB square, sorry, the cube omega B. So now let's take a look. RC, what? RC is the 2R. And RB, there's RB of 0.25, R which is 1/4R. You can plug that into formula. And the omega C and omega B, you have the relationship from that. So omega C over omega B is 1/4. So you plug that, that is the 2R and 1/4R cube, and that is 1/4. So if you just cancel the R out of this formula, that leads to the 2 cube times 4 cube divided by 4. That's gone. That is 2. So that is 8 times, what is that? That's 16. So that should be 1024. So angular momentum of C, that biggest disk, is about 1,000 times bigger than the one of the smallest disk. If they are connected by the belt, they're physically connected. And while this big disk produced the one, maybe like unilist one physical quantity, then this smallest disk should have like 1,000 times faster speed than the bigger one. Does it make sense?
Yeah.
Because this is like 4 times bigger radius, so that should have a much faster